Assalamu alaikum everyone. Today we're going to discuss about the graph isomorphism in the light of Oberoi's work. So first of all, we're going to discuss about the problem solved by Oberoi. So it was the algorithm which was represented by the Oberoi was about the detection of subgraph isomorphism in dynamic graphs. So basically, it means that identifying recurring patterns across changing state. It was about the detecting isomorphic subgraph in the real time.
As there have been many models before the Oberoi's, but how was Oberoi's model different? Oberoi's model was based on snapshot. As other models actually aggregate all the temporal information in a single graph, Oberoi's model is dynamic, which means that it works and calculates the isomorphism in the snapshots at different points. Previous models had to reconstruct isomorphism from scratch every time new information was added or every time a new graph was added. But Oberoi's model is dynamic, which means that it reuses the previous recorded and it only recalculates the part which have been changed. So other models were computationally expensive because they had to start from the scratch, whereas the Oberoi's model is more practical.
Now we will move to the evidence of solution. So Oberoi's teams compare its algorithm with Mackey's algorithms and temporal algorithms. Their algorithms were performed well in specific scenarios, but they were not performing well in dynamic subgraph systems. So Oberoi's snapshot-based algorithm provides a competitive runtime and a good time complexity look according against their solutions.
Now, as far as the code execution is concerned, I have added a snapshot that tells about the output of the code. Here it explains that the V1 vertex of H graph, which is a pattern graph, maps on V100 vertex of G graph, which is a target graph. Likewise, it also shows the relationship between its edges. Now, as far as input-output is concerned, the input is divided into three parameters: target graph, pattern graph, and window size increment. Think of target graph as a larger area, which is kind of a social network, whereas the pattern graph is a smaller area that is inside a larger area, which in our case is a target graph. Here, the window size increment refers to an integer which tells the operating system regarding this snapshots that are to be taken while executing the code. Here, output is self-explanatory, which has also been told in the previous slides, which basically tells about the mappings of different vertices, the relationship between the edges, as well as the recurring patterns or changes that might occur over time. These are the commands that are required to run our algorithm on a console.
So let's now discuss about the Borges paper. The Borges paper mainly focuses on analyzing the team's behavior in the basketball matches and their patterns of passing, and on the basis of which we could conclude the performance of a team. And its central idea is to use graphlets and transition profiles, which is actually simply the patterns in which the players pass the ball. Now this is the figure number 3, which clearly shows that Spain, which is in red, had a more complex passing patterns as compared to the Argentina. Argentina is mainly on 1 and 1-2, which is no passes and a single pass. Figure number 4 also shows that the patterns of Spain were more complex. So from this, we can conclude that that the Spain's greater complexity and variability led to its better performance. Thus, Spain's dominant performance, that was a win in the match of 95 matches, was due to its complex variability and complex passing pattern as compared to Argentina. So this is how Borges work